Welcome everybody to this week's installment of our reading group. Today I'm really excited to welcome Mostafa Elhoushi and Akshat Shrivastava, who will be presenting their work on LayerSkip, enabling early exit inference and self-speculative decoding. LayerSkip is an LLM acceleration method that speeds up inference by strategically restricting the model's layers invoked. It gives around a 2x speed up on various tasks by introducing dropout during training and early exit lost to the model to model the representations of early layers. But I won't spend any longer introducing. I'll hand over to you guys. Really great to have you with us today.
Yeah, thanks, Daniel. Thanks everyone for joining. Let me start sharing my screen. Okay, can you see the slide now?
Yeah.
Okay. So yeah, so we have two main sections in the presentation: the training like recipe and the inference solution that we're proposing. So I present the first half, and Akshat to present the second half. So first of all, just starting with a motivation. We took a Llama 7B model as it is, with like the baseline model without any modification, and we wanted to understand like what happens at each layer in a LLM, a large language model. So what we did, we applied a prompt. This is a coding prompt. It's a function header with a doc string command describing the function, and we provide to the model, and the model generates the function body. So what we did, for each token generated, we tried to exit early at each layer. So if you look here, this is the last layer of the model. This is the final output of the model. It's generating the function body it's a for loop for I in range, length, numbers. It's a nested loop. Okay. But we show here that what happens if we exit at earlier layers. So let's say what if we exit at layer 21? So only run 21 transformer layers and jump to the LM head. By LM language model head, we mean the final. So transformer consists of transformer layers. A group of, in this case, Llama 7B has 32 layers, and then a final linear layer and layer normalization. So this final linear layer and normalization we refer to as the LM head. So what we do here is we try to exit a specific transformer layer and just run the LM head and do the softmax and get the predicted token. So we see like sometimes the token can be predicted quite early. So for this token, the token length, we could have exited early at layer 12. We got for this seventh token 07, we got the predicted output. However, for other tokens, we need all the layers. For, let's say, for 4, we need all 32 layers. We need to wait to the very last state to get the predicted token. For some tokens like I, we were able to get it at layer 25. Actually, we could have got it at layer 10, but as we progress across layers, the layers were sort of changing their minds a bit here. Layer 18, they switch from I to pair, or layer 24. So in general, yes, LLMs on their own, they don't need all tokens for all layers. Different tokens can exit at different layers. But then we have two questions here. If, let's say, if we had like an Oracle predictor that can tell us when to exit, we found that on average out of 32 layers, each token average requires around 24 layers. So that's 25% improvement. However, we feel like we want to do better than that. So we have two challenges: how to know when we can exit, and the second challenge is how to make the model exit as early as possible to increase speed up. So other papers, they have tackled this problem in the field. Many papers, they add additional early exit heads, so additional LM head for each layer, and they train those LM heads to help predict earlier. And they also use heuristics such as cosine similarity between a layer's input output, or sometimes they train additional model to predict whether it's okay to exit this layer or not, and hence they make hence the inference solution requires that at each layer we exit at a different for each token exit at a different layer. So the disadvantage of these approaches is, first, they increase memory footprint because they added additional modules. Also, during training, if you're going to train from scratch using these heads to encourage the model to exit earlier, they slow down training because usually they add heads for all layers. They add additional heads for all layers. And also during inference, it becomes a bit cumbersome. Like each token requires to exit a different layer, so this becomes more challenging. So we present a solution that has a training component and the inference component. In the training component, I'll focus on how to make the model exit and how to make each token quite fewer layers, and then what Akshat will do is deal with the in inference how to make how to guarantee the highest possible accuracy when if we exit area by running the remaining layers. Okay, so for training, we modify the training recipe with two components. First, we add an early exit loss. So during training, we at some layers during training we try to jump to the LM head and predict the tokens and add a loss function for that. So that's one thing, adding an early exit loss, and second, adding a layer dropout. So basically, during training we try to skip layers stochastically, like randomly, but we have for earlier layers we have a low rate of skipping, and for later layers we have a higher probability of skipping. This way the model becomes more, we're trying to motivate the model to be less reliant on later layers, because later layers are being skipped with a higher rate during training. Okay, so starting with layer dropout, this diagram was meant to show that, dark green, they either are not skipped or skipped lightly, and the later layers, they are sort of hashed because they're skipped with a higher probability. So during training we're more likely to ignore them or skip them. And this is just like the notation of the operation. So a regular transformer layer at layer this is a transformer layer at layer L. This is the input at layer iteration T. So usually what we have a transformer layer, the output of the layer equals the input plus the operation on the input. We introduce this masking operation. So this is the dropout operation. It's 0 with probability P, or 1 with probability 1 minus P. So it's a random. This will either turn on or off the transformer layer. This probability it can change across layers or across time. The main thing we do is we make it increase across layers. So this equation is an exponential function. Basically, it ensures that at layer the first layer probability skipping is 0, and the last layer the probability is maximum. And we noticed that early layers are quite important in transformers. So instead of like skipping all layers with the same rate, it's better to make the probability of skipping of later layers higher than the earlier ones. Also, potentially, we can also add a warm up. So across time, we can also increase the probability of skipping. But we only did this for pre-training from scratch. We found that this was useful when we pre-train from scratch. If you're going to fine-tune, we don't use any curriculum.
Very, very quick question. Or maybe this is what you're about to say. I was going to say this is separate to the early loss, right? So you connect every output head to the final one, and you compute the loss on every layer, and you do the dropout on the two separate things, right?
Yes, we do both.
Okay. Yeah.
So the second point, which is the early exit loss. So here this diagram structure that at each layer we can jump to the last head and get the loss function. So try to predict the last given early layer. Try to jump to the LM head. Try to predict the tokens and get the loss using these predictions. These are just notations, but maybe just describe in layman terms. One thing we are introducing is that at each iteration we only calculate loss for some layers. You only do early exit at some layers. So we found that if we do early exit for all layers, this slows down training, and also might jeopardize or might degrade the accuracy of the last layer. We could have spent more time to optimize, to do like system optimizations to enable early exit for all layers. But yeah, maybe this can be revisited for future work. But what we did is that at each iteration we only exit at some layers. We tried different curriculum, but one of them was to do like a rotational curriculum. So basically, let's say here's the example. We only have 4 layers, so the curriculum could be at the first iteration only layers 1 and 3 will exit, but then the second iteration layers 2 and 4 will exit, and then they rotate. What we did actually for example, for Llama 7B, which is 32 layers, we sometimes only we did experiments where we only exit at 2 layers. So let's say layers 0 and 16 out of 32 layers. That's the first iteration. Then second iteration will be layers 1 and 17, and then the following iteration layers 2 and 18. So we're sort of rotating so that in this case, for out of 32 layers, we have every only 2 layers that are 16 layers apart that have an exit, and then we rotate. So we ensure that during training, all layers get to try to exit early, but at the same time, at a single iteration, only a few of them to save compute. Yeah, and also yeah.
Sorry, did you add any weighting to later layers? Because obviously you've noticed that dropout of the early layers, you should have less. Did you add a stronger weighting on the later layers or anything like this, or?
Yes, exactly. I had it in the paper. I thought of adding it here, but I thought that it will make the slides look messy. But
Sure.
do this in the paper. So basically, we actually the loss at one layer equals the sum of the losses of all the previous layers. So it's some sort of polynomial, if I'm correct.
Yeah.
So yeah, as you said, it is very important that we give a very low loss for early layers, because we don't really expect the model to do well at early layers, right? So we need so it will really penalize it a lot. Yeah, and you also add a scale that it's a hyperparameter. For some extent we use 0.1, 0.2 for earlier layers.
Yeah. It's kind of like the Fibonacci sequence or something in a way. If you're adding the previous ones, or maybe not quite.
Yeah. Yes, it could be something like that. Yes.
Yeah.
By the way, this equation was from other papers. Like other papers, they had this equation, but I think as far as we are aware, maybe we are the first to introduce this like rotational or curriculum one. We also had a graduate curriculum as well, where in the first iteration only the later layers are only exiting. As time goes on, we more the earlier layers get to experience the early exit loss. We did this as well.
Okay, makes sense.
Okay, so the question is like, when can we do this? Shall we do it pre-training from scratch, or we start with the pre-trained model? So we actually did both. We tried to experiment both and see how will our solution work. So in our paper, we tried 4 different scenarios. The first one, which we refer to as continual pre-training, means we start with the pre-trained model Llama, we did 7B and 13B, and then we try to get like a generic diverse language code data set that language models are usually trained on, and we just continue training using dropout and early exit loss. So this is the experiment which we refer to as continual pre-training. Pre-training from scratch is, yeah, we just take a model from scratch and train, but obviously we can't. It's difficult to train a language model till the end because, as you know, they require a lot of GPUs and GPU hours. So we just did this as some sort of proof of concept that we take an uninitialized model and train for a certain number of iterations with and without our recipe and compare the accuracies of both. So this was more like a proof of concept to see if this recipe can be used by other researchers or other teams to pre-train from scratch. This one here, we also tried fine-tuning on a specific domain. This in particular, we're trying to imitate Code Llama. So if you're familiar with Code Llama, they start with the Llama model, and they got a data set that's mainly code, programming languages from Java, C#, Python, whatever, and they fine-tune Llama model on code to make the model stronger at coding capabilities. So we also wanted to experiment on this type of scenario, which is fine-tuning on special domain data. And the last one is fine-tuning on a special task. We had that's a top V2 that's meant for instructions for mobile phones. And yeah, we also trained with our recipe. This was also to target there's a big research community on using things like LoRa and QLoRa to fine-tune large models on special like tasks. So we wanted to show if our recipe will work on these types of applications. Okay, so now showing the results. So here, starting with the continual pre-training one, the first one. This is the Llama 7B, this is Llama 13B. So focusing on one plot, this is the accuracy at each layer if we exit. This in particular is MBPP. This is a coding task. Blue is the baseline, so you can see the baseline blue. Its accuracy is 0, almost all the layers, and suddenly only increases like towards the end. With our approach, we have a higher accuracy at earlier layers. Okay. So tasks which we can refer to as generation tasks like coding, MBP, human eval, math, natural questions, you might notice that baseline has almost 0 accuracy earlier layers, and we have a non-zero accuracy. However, classification tasks, and this also perplexity, Wikipedia, books, the stack. Perplexity is the lower the better. So we see that we have a low perplexity, and this by way a log scale. So you can see the baseline has like magnitude of an order of magnitude higher perplexity for earlier layers. Why? With LayerSkip we have way lower. For classification tasks like Hera, Swag, Pika, you can see that early layers they don't have a non-zero accuracy. It's not that low, but you also need to remember that classification tasks are easier than generation tasks. So these classification tasks are usually like Pika or Sika. They're multiple choice questions. Usually the answer is like either 1 out of 4 possible choice, A, B, C, D. So first of all, if you make a random choice, you get 25% accuracy, right? Unlike those generation tasks, if you generate random tokens, you can get 0 accuracy. So that's why they have non-zero accuracy. For the baseline has non-zero accuracy. However, we're still doing better than it. Yeah. Another thing is that classification tasks only require to generate 1 token. By the way, there are different ways to evaluate classification tasks. Some of them just generate one token and see the probability of that token being A, B, C, or D. There are other ways. Some of them they concatenate the question with the different answers, and then see which ones have the lowest perplexity. But I mean, in both cases, it's, I would say, a relatively easy task compared to having to generate token by token. Because in generation task, if one token is incorrect, it will have a compounding error, a compounding effect on subsequent tokens. So anyway, one surprising thing is MMLU. MMLU is actually a classification task, but it's considered a very challenging one, and we're surprised that the baseline is doing well on earlier layers.
Do you see, quick question, do you see, I was just thinking, like, surely on the harder tasks, you would imagine that the baseline would probably do better because it's able to kind of make more use of the earlier layers. I guess, like, obviously this is a form of regularization to some extent, like guaranteeing that the earlier layers can solve the task independently. But like, if there's a task that's so hard that it needs to fully leverage the full capacity of the model, then maybe you'd expect the baseline to do better on those really hard tasks at the end. I mean, like on the maximum final head, the baseline would do better, whereas on maybe the easier tasks, maybe maybe then in those situations, the final performance could be better with the LayerSkip version. Do you see anything like this?
Yeah, so we did. There was a challenge that when we introduced layer dropout or early exit loss, the final layer actually does increase. So we had to spend some time to tune the dropout rates and early exit loss scales in order to avoid this dropout accuracy. But we here we zoomed here. I'm zooming in the last layer here.
Yeah.
To show that okay, with 7B we're like when you fine tune enough, we can actually get better perplexity than the. So this LayerSkip, this baseline, we get better perplexity. For layer 13B, it's not the case. Maybe 13B is slightly the baseline was better. So for smaller models, if you do continual pre-training, I think it's easier to get accuracy similar or maybe sometimes better than the baseline if you train enough. For some models, yeah, sometimes we're better, sometimes we're worse.
I guess there must be some tasks where like the baseline without this like auxiliary training does better. Because I guess maybe on really hard things that like push the capacity of the model to its limits, you kind of need the intermediate representations to be, you kind of need to use all of the layers to like do some deeper processing, and kind of forcing the earlier layers to have the output ready to go like might be a form of inductive bias that's not helpful for the task. But I guess you see kind of a bit of a mix. So sometimes the baseline is better, sometimes yours is better on the final head, and it kind of varies quite randomly, I guess.
Maybe what you're saying is like, for example, Emily is a quite hard task. The baseline is doing better.
Yeah.
I would say network question, trivia QA, they're quite hard, and math they're slightly better. But for them coding, we're doing better.
Interesting.
I'm not sure why. I mean, by the way, coding in general, especially human eval, is a very noisy metric. MVP is less noisy, so yeah, it's not clear. But
interesting.
Yeah, but I think with fine tuning, if we do enough fine tuning, we can catch up.
Yeah.
With the baseline accuracy.
Yeah. Makes sense. Thanks.
Okay. So yeah, and this is pre-training from scratch. Yeah, I'm trying to finish at half past so that Akshat can throw the ball. But yeah, we're showing this time the difference between if we train layer dropout only, early exit only, and both. We see that early exit is the main contributor to accuracy at earlier layers. In I would say in middle layers, dropout on its own can do well, but in very early, dropout isn't enough, and early exit is needed. Another thing we notice is that yeah, maybe I'll go there. Yeah, if you fine tune a specific domain, I would say that's a very promising that early layers are very close. I mean, not very close, but closer to last layer accuracy. For example, this top V2. I mean, if you only fine tune a special domain, you can make early layers become really way closer to the last layer accuracy. So so we believe that we haven't yet combined this with Q LoRa or LoRa, but we believe that this can be added to the recipe of tasks or scenarios where people want to find tune a special domain. Okay. One thing I wanted to show is this: what happens. This is like some ablation study, which we found that is quite interesting. This is just pre-training from scratch. Okay, we want to show what happens for the loss at the last layer and earlier layers, the middle layer. So the perplexity for the last layer, as expected, decreases across time. So this number of training tokens. Actually, it's a number of training GPUs, but it's equivalent to training tokens. So as you expect, when you train with more tokens and more GPUs, perplexity decreases for the last layer. However, for the middle layer, so this is layer 12. This is 24 model llama, and this is the Akshat layer 12. You see the baseline. If you don't add any early exit loss, the loss at early layers can increase with orders of magnitude. So if you don't add early exit loss and just train, the model is not motivated to predict correctly at earlier layers. And surprisingly, at earlier, like with fewer tokens, the earlier layers are quite similar to later layers. But as you train more, earlier layers become way more different from the later layers, and they diverge. So this is an interesting thing we have noticed, that when you train with more tokens, layers diverge from each other. However, if you add an early exit loss, we damp this down, and I mean, because of the scale, it doesn't show, but yeah, but layer, this is slightly decreasing middle layer accuracy. So yeah, I was hoping this slide could be motivation for researchers to consider early exit loss from pre-training from scratch, because otherwise, if you do continue pre-training, if you wait for the model to be pre-trained till the end without early exit loss, and then you do extra training with early exit, we had to spend some time to undo this effect and pull. So the more tokens a model is trained on, the more the far further away the middle layer is. So if we wanted to fine tune with early exit loss, then we spend more time to undo this effect. So yeah, and then the question is, is exiting early on its own enough? Can give us a decent accuracy? And we noticed not really. So these are two different prompts. Okay, let's start with this prompt. The capital of New York State is, and then this is a Llama 13B where we exit layer 24. It has 4 layers, but we exit at layer 24. So the baseline model will just keep on repeating alb. By the way, the correct answer is Albany. And notice that it seems that Llama tokenizer has one token for alb and another token for Annie. It was able to predict alb, but after that, it's just goes out of control, just repeats the same token. This goes back to the fact that maybe the first token could be easy, but if you add more tokens, it's could be more difficult. Anyway, what about if you use LayerSkip? Then this answer is more correct. It does say Albany. It is the capital of Albany County. It was founded by Then I searched on Google and I found there is a river called Albany River, but Albany city doesn't lie on it, so it was hallucinating here. And you see, there's some repetition is happening. There's hallucinating. It claims it's surrounded by Albany State Forest. I searched online and found that's not the case. The city has 24 neighborhoods. I searched online. I think it was 24. Instead of 24, it was 22 or 26. So it was quite close, but not exact. And the population is 40. I think it was 10,000, 45, and so on. So there are some tokens which are incorrect. And regarding coding, it looked better. So this is I prompt the model to do bubble sort. I just provide a function name bubble sort, and I ask the model to complete. So the baseline exit layer 24, it's completely rubbish. However, with LayerSkip, it's quite. I mean, it was almost there. The ranges here need to be fixed, and this anchor need to be fixed. But most of the tokens are correct. So the solution that we looking at is how to generate those tokens, but then correct the wrong ones, which is what the self-speculative decoding approach that Akshat will present now. So I can stop sharing and Akshat can share. Yeah.
Awesome. Let me quickly share. Do you all see my screen?
Yeah.
Okay.
Awesome.
Cool. So thank you, Mostafa. And Mostafa talked a lot about training, and we're able to do a lot of impressive things with the earlier layers of the model. But the goal now is how do we really go after inference? So Mostafa left you on a little bit of a cliffhanger, but before we go into that, wanted to go over a little bit of background. Cool. So generation's composed from a transform model composed of two key stages. There's the prefill stage where we generate like all the states from a prompt, and then there's a step-by-step inference stage where we generate tokens sequentially, which is autoregressive decoding. So going over them independently, the first step here is prefilling. You can see an example transformer diagram on the right here with 4 layers, and we'll use an example like this throughout. What this stage does is it leverages the fact of the transformer being a naturally parallelizable architecture. So what we can do is we can feed in all of our tokens beforehand, like T1 through T4, and we can in parallel compute all of them because everyone takes a dependency on everything to the left of it. It's this causal structure that transformers use. So going through this is actually the same as had we gone through it sequentially because we're using the same amount of information at each step. We're masking out a triangular portion of it, so there is some amount of wasted compute in the attention, but it's fine because we can parallelize it all. It's really, really fast to do this in comparison to autoregressive generation because it's more or less not as strict on sequence length growth. There are some quadratic functions of attention in here, but that's about it really. And we can get pretty clever on how we speed this up. So pre-filling, and this is often done for the prompting stage of a model, is something that's very fast, and we do it for training too. So the thing to take away here is it's focused on parallelization. Autoregressive generation takes us a step further. And what we do is we have to generate each token conditioned on the one before it. And so in this case, you essentially are forced and bottlenecked by a sequential decision-making process. For every token, let's say T3 here, I'll feed it into my model. I'll get a distribution of what the next token should be. I have to select that token and then feed it into my model, which makes this linear in decoding cost. And this is the expensive part of autoregressive decoding. So we start with some prompt tokens, we feed them in, and then one by one, we generate every token in the output. So this is linear in length. Now we can speed it up a little bit when we generate every token that actually when we're producing T4 here, we don't need to recompute T1, T2, T3. A lot of the transformer is just point-wise computation, except for the attention layer, which is contextualized across the entire sequence. But if we get clever, we realize that the attention layer, we don't need to recompute everything. The key value states that have been saved from the prior, the computation of the prior tokens can be cached, and then we can reduce the amount that needs to be computed here. So in this diagram here, when we're computing a single token, let's say T4, everything in dark green is what's actually computed during a single forward pass. Everything in light green is cached, which can speed this up a bit, but you're still bottlenecked by sequential decision making. So what folks have done here in the past is they've looked at speculative decoding. And what it really comes after is you have two primitives in generation now. You know, pre-filling is really fast, it's parallel, but it can't make decisions. It can batch process a longer context, but you can't go and generate something on top of it. And then you have autoregressive generation, which can force you to have this reasoning step or this generation of every token in the output and actually generate something meaningful, but it's very slow, it's linear in cost. So it was proposed to do this back in seek-to-seek modeling days and decoder modeling days, and become really, really popular in language modeling now, is speed this up with speculative decoding. The main idea being here that you take a smaller model on the left here, and you use it for autoregressive generation. So that second step we talked about, you do it token by token, it's linear, but the cost of each token here is a lot less. Like we'll go with 2 layers instead of 4, for instance. We'll generate an output, and we'll go T1 to T4 is what we'll generate step by step. When a certain limit's hit, we'll send this off to a larger model. This is the main model that we wanted to replicate quality for. And what it'll do is it'll use its pre-fill and parallel generation functionality to take the entire draft sequence as input, T1 through T4, and produce what its predictions were for each of those tokens, fully in parallel. So it'll produce T1 prime, T2 prime, T3 prime, T4 prime. And everywhere that they line up, and as long as they line up in sequence, we know that we're verifying everything that the smaller model has done. So in the best case, you'll realize that everything is correct. And now you're guaranteed that your small model had the same accuracy as a large model. So you have the large model quality now, but you didn't ever do autoregressive generation from it. and you can go forward to the next window of tokens you want to generate. But if anything goes wrong, let's say we're doing 5 tokens and the third token is wrong, we can tell the small model, actually, you should have done this for the third token and give it the correct output, and then ask it to continue generating again. And even from there, we got 3 tokens that were coming from a lot lower latency, and we verified them all using the larger model. And the idea is, as long as there's good consistency between your small model and your large model, you can get pretty big speed ups, like 2 to 3x improvements without any quality loss in speculative decoding. So this is a pretty key component in speeding up large language model inference right now, especially on server. Like, you'll see it deployed in several different places. Actually, I don't think it's called out, but if you take a look at, let's say, ChatGPT, for instance, you'll see it's decoding in blocks at the time. So you get a pretty good hint that they're doing some kind of speculative decoding as well. So speculative decoding works. It's fantastic. Would strongly recommend it. But it comes up with 2 key limitations that we were looking at. So one is that if you're not in the language model training business and you don't have hundreds of thousands of GPUs to be doing this all the time, training another language model is not the most trivial task in the world. It's pretty expensive. If you're doing it from the community, you're bottlenecked by what everyone else has. And it's actually a pretty big trade-off in looking at what's your task, what's the latency you want to hit, what can you afford to deploy, what are the 2 models you can use. Another language model is non-trivial overhead. The second thing here is that if you take it a step further and you go onto resource-constrained devices, like you're going to start running LLMs on your laptop, on your cell phone, on other maybe AR devices, which is the space I was coming from, you're really, really memory constrained. So fitting an LLM itself is a big challenge. Fitting another one to do speculation is just prohibitive. You can't do this. There's nothing to be done here. So the question is, how do we enable the wins of speculative decoding within these 2 constraints if we're building what we believe to be a more efficient paradigm into training language models? So the key insight is going back to everything Mostafa dropped about in layer drop and early exit, and it's to view layer skipped models, or our full recipe here, as supernets. And so if you layer skip train an LLM, what you're really doing is, given an n layer model, you're producing n different models you can have within it. So, and each of those models gets progressively better quality at a higher latency cost. So you can now understand that, okay, if I want a model that's this quality versus this latency, I can just select it from a single training run of a layer skip model, and I can build this out. It's also really nice because compared to like sparsification, quantization, other methods, all n different models are the exact same transformer block that's being used. So if you've developed really fast kernels for inference, if you've done fused operations, all you really need to do is that this is just another transformer model. It fits in right out of the box. You can train it, fine-tune it, deploy it however you want to, all just from training a single model with LayerSkip. So the real question is, can we use this information from smaller models and use it as a supernet to remove the draft model as a separate model, but use one of these subset models instead? And we term this as self-speculation because our LayerSkip supernet is using a subnet of itself to do the drafting and a different subnet of itself to do the verification. So it's all within a single model, and you can control the trade-offs here. So going into what the algorithm here looks like, the first step here is that we use the smaller model for early exit as our drafting. So we take our main model here, which is the large one shown here as 4 layers. We pick any layer to exit. In this case, we picked 2. You can pick any layer you want. We do early exit inference from the first 2 layers here, or E in general, and we skip the rest of them. So these are still in memory. We're just not doing any inference on them. And then we compute the outputs, and we get our draft sequence predicted here. Going into the verification stage, what we do is we run it through the entire model. So we compute every token fully in parallel, and now we're guaranteed to have the output quality that the final model would. And the same conditions of speculative decoding apply, where we look at the acceptance rates, the rejection criteria here, how we can just borrow everything identically, and we get this aspect of the memory saving of not having a second model. It turns out you can take this one step further, specifically because we do this sequential early exit mechanism, where your first E layers are guaranteed to be in order in our mechanism. So we're doing layer 1 and layer 2. We don't do something like layer 1 and layer 3 for this. When we do the verification stage, you've actually already computed the hidden states that are going to be for a good part of this model. So the first 3 tokens here, which was our draft model, we have already computed, and we have the first 2 layers for. So if you get into something like Llama 30 billion, where you have 40 layers and your early exit's 20, it's actually non-trivial to save this amount of compute, because in verification, you can cut nearly half of the compute out. And this can make it quite a bit faster. So this also takes it, not only does it make it a bit faster, so here are some numbers here that we get like 10% speed up doing this way, it's also additional memory savings because you're maintaining a single KV cache. So all the tricks you're doing for KV cache compression, attention sinks, etc., they all can persist in the small model and large model. So you have speculative decoding and not only one model that you're able to use, but a single KV cache too. So you really have very little memory overhead over traditional unrestricted decoding, yet you can start to get the speed ups of speculation. So just to further emphasize my point that we're just becoming very, very clever on how we use LayerSkip models, on the right here is pseudocode for the entire self-speculative algorithm, and it mirrors exactly speculative generation. You have a step here that will use the earlier layers to draft tokens. What it does is it uses this thing called forward early, which just exits earlier into the model and saves the KV cache and updates it throughout the drafting process. Your second stage, you use the remaining layers, which is what we talked about earlier, where we don't compute the first n. We only compute the ones after that, with a special case for the last token, because that one technically hasn't been computed yet. But essentially just normal transformer forward pass. And we can compute what's been verified. We can see what's accepted, rejected, and we update the KV cache. And then we iterate on this over and over again until we've hit end of sentence or maximum tokens, however we want to stop generation. But it's really straightforward to plug into any speculative decoding framework. The key thing to note about this tool is that there are 2 key parameters that dictates what the quality of your speculative decoding will be. You're guaranteed, even if your model was complete garbage and produced like just 0 output, that you'll have the same quality as your full layer model because of the verification step. So quality is not something you'll really control, but it's really going to be about the tokens per second that you get here. So there's 2 things you can select. You can select the layer to exit on, which is the early exit layer. If you pick something that's too low, the model is going to be too low quality despite being fast. It'll fail too many verifications. We'll keep just running the larger model over and over again, and we'll just eat up the cost of this being the same as autoregressive. Too high, and it'll be accepted more, but you're going to be running a more expensive model each time. You'll start losing out the win, so you need to find the balance here. The other thing is the number of speculations, or the size of the draft sequence that you're going to validate. There are heuristics to do this, and there's a lot of work in speculation that you can rely on. Like Hugging Face is something like whatever is accepted, if everything is accepted, you multiply it by 2, or you add 2 or something like this, and you shrink if it's rejected. And you kind of be dynamic about that. We kept it simple, and we just kept it to be a static number that you can work with. But if you pick something that's too low, you're essentially just running autoregressive generation through the verification stage. So you're not really saving anything, but you're not going to be worried about in the case that you got something wrong, which is a concern if you're too high. Like if you had 10 tokens and you fail at every 2 tokens, you're wasting 8 tokens from your small model. That's cost you're still going to be incurring. So the balance of these is something to get right in speculative decoding in general, with this early exit one that we've thrown on as an additional parameter here to control. And what we find is it really depends on the complexity of your task, the data and domain that you care about, and other properties there. So starting off by taking a look at that, what we graph here is graphs for the 7 billion model that we've continually trained in 2 domains. This is human eval, so it's just more of a coding domain. Not more of a coding domain, it is a coding domain. I believe it's entirely Python, I think. The second one is CNN Daily Mail, which is a summarization task that's more your general natural language generation. So on the x-axis is the layer that we exit at, and we range from around, I think, 0 to 20 here, and then the number of speculations, again, ranging from 0 to 20. And what you'll see is that in coding tasks, we actually require a lower number of speculations, but still around this like 7 to 8 layer exit's pretty optimal. So the darker the color is here, the higher the tokens per second. So the dark regions is really what you want to optimize for. So something about coding puts us into like, yeah, less speculations, but around 7 to 8 layer inference, early exit inference. And in summarization, you end up with a slightly different pattern where for the 7B model, 7 to 8 layers is still roughly the sweet spot, but the range of speculations can matter quite a bit more. So you want to go a little bit later. So I think more and more is getting accepted here. Longer sequences too in summarization is probably taking artifact. But this is where you end up with slightly different optimal sections of what's going to be your fastest generation here. This correlates quite interestingly also with acceptance rate. So here's the same graph, except we're graphing the density of acceptance rate here. The darker the color, the higher the acceptance rate. Intuitively, if you had a fixed model size, maximizing acceptance rate is what you want to do, and that'll directly lead to your speedups. But there are some degenerate solutions here. Like if your number of speculations is 1, then your acceptance rate is probably going to be pretty high because you're pretty likely just to get it right. But you're not going to get any speed up. If you have your early exit be later into the model, you're also going to get a very high acceptance rate. So you'll see these dark edges around this map here. That's this is the degenerate solution that's not going to offer us the speed up from earlier. These points here are the same ones that we graphed earlier, which is right around here is the optimal region for human eval. Right around here is the optimal region for CNN Daily Mail. And you'll see it's right on the border of what's becoming into high acceptance rates here. That we're just transitioning into these darker colors, but we're still in this realm of what's earlier in the model and later in speculation than the degenerate solution. So a trade-off there to keep in mind, all consistent with just acceptance rate and tokens per second. Now going into results, I mean, the spoilers, it works pretty well. The really nice thing that we saw about this work is that a lot of the speculation work, and I think primarily because of the second model it requires, often uses much larger models to justify their wins. So you'll see 13, 30, 70B models getting sped up with speculation decoding quite a bit. And in particular, this is work that we were inspired by called Draft and Verify. And they were able to skip specific operations within the model, like layer, norm, and such. And they could learn and mask over which operations to skip. And they started to see a lot of big speed ups, also self-speculatively at larger scales. One benefit we got is that we were also able to go the other side, that our skills would also scale down with the model too. So if you were working on edge devices, or if you've seen like something like Phi and OpenELM coming out from Microsoft and Apple, going down this route of cell phone-based inference, you're going to be working in the 1 billion range, 3 billion range, and our wins persist at that scale too. We're seeing like pretty competitive speculative decoding rates with Draft and Verify, the other speculative decoding approach. So we're getting 1.8x improvement where they were getting 1.5. We're a little bit lower on other abstractive summarization like XSum. So we're roughly competitive in that space, but we do see pretty good speed ups throughout. And so the results on these different tasks here after some tuning on what's the right speculative decoding parameters. So that's one thing that is required from method, but yeah, working pretty well. Token acceptance rate is pretty reasonable. You see about 50 to 60% is what we need, 50 to 70%. And given the trade-offs that we're seeing, that's roughly enough to get the 1.8 to 1.5 speed up across tasks. So the next thing we take a look at is if we had pre-trained from scratch. Sorry, I should have clarified all the earlier results for continual pre-training within a domain. If we pre-train from scratch, we can get even better improvements. So taking a look at Llama 2 7 billion, we can go from 1.8x to 2.2x improvements on CNN Daily Mail summarization. So if you start doing this throughout the training process, likely you'll see even better improvements here. As Mostafa mentioned earlier, we were bound by compute scale, so we didn't run these throughout. So it's something we're continuing to work on. And our paper is kind of live. You'll see it get updated now and then with even better results because we're continuing to push on this direction and we're continuing to scale things up. With that said, Mostafa, I can hand it back to you. If you want, I can also just do next slide.
Yeah, you can do next slide.
Oh, sorry.
Yeah, so basically, like as a conclusion, we were able to increase accuracy of earlier layers without adding any additional modules. We like during training, we trained the model and the LM head to predict tokens without adding any additional modules. And for speculative decoding, we propose a self-speculative decoding approach that doesn't require any additional layer. So it has less memory footprint, and it also reuses the KV cache of earlier layers. And we believe that there's a potential that this will lead to even bigger speed ups if it's included when training from scratch. Um, yeah. So the next slide. Yeah, for future work, yeah, as I said, we can try to scale up with more GPUs and larger models, and because it seems that when for pre-training from scratch, larger models and GPUs will do better. For continual pre-training, it seems that small models will do better. It's the other way around. And also for fine-tuning, we can try to combine it um, with other techniques like LoRa to improve access of earlier layers. Yeah. So yeah, that's it from our side, and we're open to any questions or comments.
Amazing. Well, thank you so much, Mostafa and Akshat. Let's give a big round of applause virtually for that amazing talk. Really, really interesting. So yeah, I mean, I guess if there's any questions, then feel free to raise the hand, and yeah, Akshat and Mostafa can answer. I can certainly kick off if no one has anything to start off with. Okay, I'll kick off then. So first question, I'm kind of interested in the motivation. So obviously, the early exiting lends itself very nicely to the self-speculative decoding. Kind of which motivation came first? What was the motivation to try to do speculative decoding with one model, and then the early exit was kind of implemented to try to achieve that? Or were they really kind of two separate pieces of work? I mean, it seems like there's innovation on both fronts. You know, this could even be two papers, to be honest. It's really, really interesting. But what motivation came first to trigger it?
I think we tried to see that if you can exit. Like first, I was presently looking into if you can whether should you skip intermediate layers or exit earlier, and then I tried to look into to make this answer. Also, I was trying to see if you can improve earlier, if you can skip layers in inference without having to fine tune the model.
Yeah.
But I eventually reached some sort of conclusion that if you want to get better speed outs, it's better to modify the weights and let's fine tune or train from scratch using it.
Yeah.
So, and also we did have the option of considering using like heuristics or an additional model to decide when to exit. But this idea also came out that speculative decoding was a hot topic, especially a while ago. So we felt maybe instead of coming up with and this idea came out that if we can think of, instead of doing speculative decoding with a big model, small model, a subset of the model could be the small model. So I mean, we're doing brainstorming and the ideas were coming here and there. So yeah.
Mostafa, just to add a little bit onto what you're saying as well. It also came together that way in like parallelly progressing into a single work. So Mostafa at the time too, like everything he's talking about was focused on improving LLM quality and pre-training. On my side, I was working a lot on constrained devices and memory efficiency. The main thing that I was pushing here from my side was this hypothesis of dynamic compute, which is especially if you're on device. That I was working on a lot on code generation tasks, and you'd spend a static amount of compute generating something like a syntax token as much as an API token. So I was exploring how could we get around in generation this idea of static compute through dynamic compute. Seeing if there was a different way we could reduce compute per token. Mostafa had shown layer drop, LayerSkip to be successful, and we kind of came together to put together this entire end-to-end package of just speed up.
That's amazing. I think a lot of the best works often come with some kind of intersection and like cross-fertilization of ideas. It seems like they like marry together really, really well. It's interesting they started from two different motivations. I guess another question is like, so obviously the early stopping is a really nice approach to then do this self-speculative decoding to avoid the need of having a second model to do the speculative decoding, and that brings speed ups in and of itself. obviously you compared to other works that do early stopping and actually have the dynamic early stopping at runtime. It seems like the early stopping right now is not built in at runtime. You obviously you did these graphs where it's kind of just fixed ahead of time where you do the early stopping, and the way the speedups come in inference is through the self-speculative decoding. Do you plan on doing any work? I know that you brought up these downsides, that having a separate head per layer to make this decision or something adds overhead. So maybe you just don't think this is a good direction. But do you see there being ways of using this with explicit early stopping as part of the inference?
I can take this one. It's a great question. You're right. We were motivated by we wanted this principle of no additional parameters. We did try additional model heads and such there. And I think Mostafa can speak more towards the results on that one, but skipping forward a little bit, we tried the models there. Sorry, I lost my train of thought for a second.
It happens early in the day.
Oh, yes. A big motivation for us too was being able to realize the wins and share it with the community. So one concern that we had was that if you had dynamic inference at different exit points, I do personally believe that's a very, very strong direction and something we should take a look. Make sure that's from Google did the same thing and really able to do a lot there. The concern that we had here was that you'd have to come up with custom attention mechanism, custom KV caching. What happens when you skip one layer, but you want to verify that the entire thing? You did fuse kernels, it's not going to pan out. So the nice thing about this work is that it's really easy to plug into everyone's framework. So it's something we wanted to share with everyone. But I do think that static exit points and something Mostafa and I talk about all the time is a bottleneck of our approach and something we'll work on breaking.
Yeah, no, makes sense. I also, to be honest, do think that I actually do find the fact that you can do this self-speculative decoding more interesting than I think I would have found just like naive early stopping, to be honest, like this decided dynamically. It's really nice that this plugs directly into a lot of the work that's been done and just enhances it. But yeah, it does seem like if there is ever a token where 20% into the depth, you've got the right token. And if there was a way of just knowing that, it feels like you can push the performance even more with something. Maybe you don't need a decision after every. Maybe you need at the 25th, the 50th, and 75th percentile, just some decisions or something like this. But yeah, do you have any other thoughts on this, Mostafa?
Definitely, it could be done for future work. It could be a separate paper. But I felt like when I looked at the paper that do this direct stopping, they either train an additional model that predicts when to exit, or they do introduce other hyperparameters like when to use some heuristic like cosine similarity, and then they try to so it's additional hyperparameter we need to introduce. What is the threshold for this heuristic that we should stop at? And I've even seen for each layer they have a different threshold, and they calibrate the best threshold for each layer. So it was I would say out of more work, but it's doable. It might, combining it with scheduling could lead to even bigger speed ups.
It feels like I've not gone obviously anywhere near as deep as you guys, but it feels like it could be an extension of the self-speculative decoding in a way. Like part of the verification you're doing there could lead into a decision mechanism that verifies can I just use the token directly? It feels like there could be some extensions there perhaps, but anyway, super interesting.
But also the interesting plot that definitely when you increase layers, the acceptance rate will increase, but at the same time it goes against performance, right? So yes, let's say if we do introduce a dynamic exit heuristic, and yes, this increases the acceptance rate, but I'm not sure how it will affect the speed up. So it is a trade-off, and it's worth exploring.
I imagine you could get these similar kind of graphs, these really interesting graphs about the depth and the number of attempts needed to get the sweet spot of maximizing tokens per second. I imagine there might be some similar graphs there if you had early stopping decisions as well. Anyway, but I'm really interested. I won't hog too much time. I know Kato has a question. Unless that was a mistake. I don't know if that was meant to be an applause. Do you have a question, Kato? No, maybe that was a mistake. Any other questions from anybody?
Yes.
Oh, you do? Okay. Go ahead.
I wanted to ask a question concerning security of the model. Yes, I don't know if my internet is okay. I may have to test it if you're not hearing. Okay, given that the LayerSkip allows for early exits. Does this feature increase the risk of the model inversion attacks, where sensitive information can be inferred from the model's outputs? How did you handle such risks?
Yes, okay.
I haven't thought of it. Maybe Akshat can mention, but I would. There's an interesting paper called Selfie. I'm not sure if you've seen it, but they do show. They didn't do exactly early exit, but they did some manipulations. But they do show that, let's say, if you ask the model something like, "How can I how can I build a cocktail bomb?" The last layer, it does say, "I cannot tell you because it's dangerous." But I think they show if they manipulate or exit earlier, or they take the embeddings of one layer and push it to another layer, they can actually make the model say, "Yeah, here's how to do the bomb." So, but yeah, I actually could, but we haven't thought of it like in terms of security. What happens if we exit earlier? Yeah.
No, it's an interesting question. I guess it's not going to be. I guess the fact that you're doing this auxiliary training so that the intermediate layers are like able to give the output would mean that you're kind of seeing less of the hidden state and something that is a bit more like output friendly or something. So maybe there's a bit less like vulnerability there, but yeah, it makes sense. I know we're running out of time. Any final questions from anybody at all? Don't want to take too much of the day away. Okay, no, well, in that case, yeah, let's have another big round of applause from Mostafa and Akshat. That was a really, really interesting talk. Yeah, looking forward to seeing where this work goes. I'll obviously keep my eyes peeled for potentially future works, adding LoRa, doing it on bigger models, maybe doing some early stopping as well. Of course, we'd love to have you, have you again. I'm sure you're going to keep doing, yeah, lots of incredible work. So we'd love to follow along and maybe have you join another session at some point. But it was a real pleasure to have you both with us today.
Yeah, thank you, and thanks everyone, and thanks Daniel for organizing it. Yeah,
of course.
Thank you.
Thanks a lot. Have a great week, everybody.
You too.
Bye-bye.
Bye.
Thank you.